in there. So this homework, again, not all the code is given to you, but you should be able to figure out what the right regression to call in your field line. So it's not that much to do. If you read the documentation, you should figure out what to call. Okay, so it's a fairly short homework, but any questions about that? Okay, all right. So have people heard of this thing called Bayes rule? Have people ever seen this thing called Bayes rule? Have people taken probabilities in this Bayes rule? Okay, so we'll go a little bit slower here. Bayes rule is actually a very, very important rule. It's quite important. And it's basically a way to use prior. Okay, so you know something that's outside just what the data tells you, and the idea is you want to take advantage of the base of this Bayes rule. Okay, so this is true. This is a way to think about priors. Right, so you know some information. How does knowing sort of the prior means some information you already know? How do you think of the information you already know? How do you incorporate that into a classifier, into a decision process? Okay. So this following example actually happens quite a bit in power systems. So what we care about nowadays is electric power transformers failing. When we have equipment problems in the grid, in the distribution system, for example, most of the time is some transformer having some issue, right? So you have transformers failing. And the reason is our transformers are designed to have a life, to last about 40 years. Right now in the grid, all the transformers are put into the grid 56 years now. So they're right at the tail end of their lifetime. and they're failing more and more often. And the idea is there a way to determine if the transformer is more likely to fail or not? Okay, so this is actually a quite relevant problem. So what you can do is you can collect the following information. You can look at all your transformers, and you can say that 10% of transformers fail. Actually, before going on, sorry. So how much is a transformer? Just to make sure we have a context of this kind of problem, what people care about. So transformer are things basically that step up or step down voltage that you have in the system. Any idea how much this equipment costs? A transformer cost, electrical transformer. So why do we care? Like transformers are failing. This is a quite relevant problem we have. Transformer takes high voltage, right? Transformer to low voltage or low voltage up to high voltage. How much are these things? Right, so this thing can go up to hundreds of millions of dollars. So if you ever go to South Lake Union, if you drive and you basically you come up I-5, you go on Danny Way, there's a transformer station that's about $250 million, housing some transformers. So that basically blew our entire budget for transformers for the next 20 years. But anyways, these are expensive things. We don't have that many of them, so if they fail, it's actually a big deal, right? So we care about this because these are sort of the core infrastructures we have. Okay, so and again, they're starting to fail, so you observe that. So then you can say, 5% of transformers experience high current, right? So we have a group of transformers, 10% of them, tend to fail at any time. Then you look at how much current is going in, 5% of the transformers, at any one time experience high current. Then you can observe, so within the failed transformers, %7 experienced high current. Okay, so these are the data typically you have as a utility. You look at your equipment failures, you say, okay, some percent of them has failed. You have now a guess that, okay, maybe high current causes my equipment to fail, put more stress on them. So then you go to the things that failed, you actually observe, okay, 7% of them did experience high current. So now the question, what you really are after is asking the reverse of this question. So now your question is, suppose a transformer has high current. What is its chance of failing? Okay, so this is a typical question that if you work for any utility industry, you work for any utility, or any time when you have equipment that can experience failures, you have a question like this. Okay, so you have a guess, basically. You think, okay, high current can lead to failures. And then you ask the question, if I have a piece of equipment and it is experiencing high current, what is the chance of failure? And the data you collect, it does not directly answer this question. Okay, what data you have is, if you don't know anything, 10% of them fail. You know the percentage of them that actually has high current. Within the set that failed, a little bit higher chance of experiencing high current. You want to turn this around. You're looking at transformer saying this transformer has a lot of currents. What is the chance of this thing failing? Okay, so this is the question. Now you got to ask very often in practice. Okay, all right. Is this question clear? This guy's asked a lot. Okay. You care about this event, right? Transformer failures. You think there's a cost, high current. You want to ask, given this cost, what is the chance of the event you're interested in happening? Right? Okay. So I guess is this higher than 10% or lower than 10%? Okay. So if I don't tell you anything, it's 10% failure rate. That's a sort of blanket failure rate. Now I say, okay, this thing actually experiences high current. What is the chance of failure? Is it higher or lower than 10%? Is it more likely to fail than say the normal transformers, or less likely to fail? Right? So the basic idea is you would think this is more likely to fail, right? Because if you look at the class of all transformers, only 5% of them has very high current. But within the class of the failed transformers, 7% of them has high current. So this is sort of somehow within this class of failed equipment, it's more likely in some sense you have high current. So the inference trying to draw is this maybe is a cause of failure. Right? Maybe having high current actually, given that you have high current, it's more likely to fail. Okay, so the idea is now based on how do you compute this failure number? How do you compute this number? Okay. All right. So is the question clear? Is the question clear? Okay. All right. Is the question, right? So is the question clear before I go into answer? Base 2 actually can get a bit tricky. It's very simple. It's basically 3 ratios you're playing around, but get a little bit tricky, which ratio is which. Okay, so again. Okay, so is this, again, is, okay. So let's try this again. So if you, so 10% is a base fail rate if you don't observe anything. Right? So if I give you I have a bunch of transformers, I tell you 10% of them fail. Now I pull out a random one to say, what is the chance of this thing failing? It's 10%, right? This is the base fail rate. Okay. So now I tell you, hey, my transformer is not a random transformer. It's a transformer that has some property, has some high current going through it. Is this more likely or less likely to fail? If so, by how much? Okay, so that's a question you want to ask. Okay, so there are many questions like this come up in practice. Where, yeah, sorry, right, yeah, yes, sure, but it's higher than the normal percent. In all the transformers, only 5% has high current. Right? So this is still higher. Right? So again, the intuition is maybe high current is more likely to cause transformer to fail. Right? So this is basically, it's like the medical study, you have things like this. As let's say within the population, 1% of the population has cancer. Right? Within the population, maybe 0.5% of people smoke. Then you look at the people who has cancer. You say within this people who has lung cancer, 2% of people have smoke. Right? So those are the numbers you can get. It's very easy observation you can get. Now your question is, does smoking lead to cancer? Is smoking more likely to cause? If you smoke, does it make you more likely to have cancer? So base rule is trying to answer this kind of question. Okay, so you observe outcome, you're interested in this case, failure transformers. You have some cost, right? You notice there may be some cost here. And the idea is to compute the probability of if you have high current, what is the chance of the problem failure, of the transformer failure? No, it's not that easy. It's not that easy. But is the question clear? Right. So again, if this is hard, think of the cancer example. Okay, so The equivalent example is you can think of, so you can think of equivalent example as, again, if you have cancer and then what is the chance of, right, so given, right, so if your question really you want to ask for example, for the cancer examples, if you smoke, what is the chance of having cancer, right? You cannot observe that directly. You cannot give the population, you cannot let everybody smoke. Wait for 20 years and see who has cancer, right? So you cannot directly observe. Similarly, for the transformer example, not that many things experience high current, right? You cannot just look at all the transformer that has high current and wait for this side to fail. You don't have enough data. Okay? So you have to use all the data you have in this case and try to answer this question. Okay? So is the question clear? Still, let's make sure the question is clear. Okay. All right. Okay. So you have some cost and understand, given this cost, what is the probability of something happening where you don't get a direct observation, right? So this, again, the hard thing about smoking leading to cancer is you cannot take the population, give half of them, let them smoke, half of them don't smoke and compare the result, right? You just don't have that kind of data, okay? You have this sort of observation data you have. So in a bit more terminology here is basically you say that we have events. Okay, so in more probabilistic terminology, we have events A and B. Okay, we have some events A and B. So we want to think of, again, is to think of A is failure, B, let's say, high current. Well, we can observe it, so that's the probability. So PA is the probability of A, PB is the probability of B. Okay, so you have some probability observing this kind of events. Right, so this you would know. And then you have the following probability you can observe. Okay, so you have P B given A. Now, what this means is suppose A happens, the probability of B. Okay, so this is written as P probability of B given A. Okay, so you read this way. What is this probability of this event happening given that I already know the other event already happened? Okay, so P given A. So this in our example again is probability that you have high current given that you have failed. Or the probability that people have smoke given that you have lung cancer. Right, so it's these kind of probability. So you know this probability. Okay, right. So you observe this probability. So the question becomes, can I now turn this condition probability around? Okay, so what is A given B? Okay, so you observe all these things, you can compute these probabilities. What is A given B? Okay, so this is the question now you care about, right? So so if you already have lung cancer, whether you smoke or not is not that predictive. We already have lung cancer. Turning this around is not a question you want to ask. If you smoke, how likely is it you have lung cancer? Okay, so similar with equipment failure. If your equipment already failed, after the fact you figure out you have high current, it's not all that actionable, right? The thing already failed. However, if you observe your transformer has high current, if you know that is more likely to lead to failure, You can have an action you do. You can back out the current. You can upgrade the transformer. You can reduce the load. You can do all the things. Okay? So really what happens in practice is normally that PA, PB, PB given A is easy to measure, but not directly useful. The useful probability to know is PA given B. And you want to figure out this number when this number is given the other things. Is this clear what we're trying to do, right? So we want to basically base rule, the whole idea of base rule is reverse this probability. Okay, you observe some conditioning, you want to reverse this. This will become a very simple formula, but many people get it wrong, or somehow do not sort of know there is such a thing as a base rule. Okay, so this is what we want to compute. Right? So what this really boils down, so you can write the sort of graphically what this means, right? So graphically is, imagine that you have some events, this is A, some other events, Venn diagram, you have B, right? So a question, right? So then the thing in the middle, right? So this is, for this things A happens, for this things B happens, and the thing in the middle is where A and B happens. Okay, so this is written as A and B. Okay, and the basic idea is basically compute what the probability of A and B is in two different ways. Okay, so now we want to look at the event that both A and B happens. Okay, right. So this is in the cancer cases. This is you have cancer. This you have smoke. We want to find people who both have cancer and have smoke. Okay, so this is the intersection of the two events. Okay, so you can compute this following way. The probability of A and B happening is the following. That first, let's say that, well, A has to happen, right? So A and B happening, A has to happen. And then you multiply this probability, once A has happened, this is the probability of B given A, that A has happened. Okay, so this is just a so-called chain rule, chain rule probability. Saying that for event A and B to happen, A has to happen. Once A happens, B has to happen. So this is the product that gives you the probability. Okay. Any questions about this product rule? Right, so this is base rule. Right, so this is one way to express this probability. Okay. Now the trick comes to say that, well, there's another way to write A and B. This right, probability A and B. For probability A and B to happen, another way to think about it is B has to happen. Right? To event that B has to happen, and then A has to happen given B has happened. There's two ways to write it. So this same number, you have two ways to write it. This basically gives you the equation. In this equation, both way of the conditional probability happen. This is the all there is to base rule. You observe that to turn this conditioning around, you just observe there's a way to derive the same quantity, PA and B. Right, so here you have, so we have, you just equate those two equations, right? They compute out to be, they give you the same number. So PA given B, this is PB given A times PA divided by PB. Okay, so this just comes from this equation. This is again all there is. Basically. So if you know these three probabilities, you can find the probability that you're interested in. All right, so any questions about this math? Again, this is just base rule. This entirely is what classical base rule is. Okay, and this is quite useful. Again, this rule is surprisingly useful. Okay, so let's go back to our example, right? So we have, let's say the event A is a transformer failure. B, this is high current. B given A is high current given that the transformer has failed. Right, so it's the transformer already has failed, right? So we have all these three numbers we have, and want to compute that A given B. Okay, so we want to compute the conditional probability of A given B. So this conditional probability is okay, so your conditional probability, this is P, that your transformer will fail given high current. This is PB given A. This is 0.07, right? 7% of transformer that failed has high current. Okay, so this is 0.7. Each of them failed 10% of the time. So this is 0.1. In your entire fleet, about 5% of them has high current. This comes out to be about 0.14 or 14%. This is the sort of straightforward application of base rule. Okay. So now you can answer, suppose you're high current, you'll fail about 14% of the time. Whereas for the general population of transformers, they fail about 10% of the time. Okay, so indeed, you're more likely to fail, and that's why you can directly compute what this probability is. Okay. Right? And this again is used all over the place. Right? So this is much less fancy than what other data science rules you have. A lot of times you learn base rules in high school, but turns out in practice, often you end up using base rule. Right? Just because often what happens is you get to observe this one, this one, this one. You really want to turn this around. And then there's a very simple calculation. You can turn this probability around. Yeah. No, not happening at the same time. Is they both happen. Right. Yeah. So that's fine, right? So here, not both event doesn't, right? So sometimes A happens, B doesn't happen. Sometimes B happens, A doesn't happen. What we care about is A and B. Right? That's precisely how you derive this. Right? So that's what makes it hard. That what makes base rule non-trivial. Right? They always happen together. That's not very interesting. Base rule is only interesting if given one other may or may not happen. Okay, so as with all probability rules, this is derived basically for gambling. You observe some good outcome, and you want to ask, what can I do to improve my chance? So this is, again, derived from that sense. But this has application all over the place. This is normally when we have something that fails or some outcome interesting, you apply base rule. Okay? You have to just apply this so-called naive base rule. Okay? So this is sort of fundamental, sort of very fundamental tool for base rule. So this is used all over the place. This is all over the place. And so another example, again, to hammer home where this can be used, is base rule is basically the first spam filter people develop, actually. So even today, a lot of spam filter is based on base rule. Right? So what happens is the following: is so let's say you want to make a spam filter. So what do? People get emails, you click, this is spam, right? You use Gmail, Gmail asks you to report this is spam. What does it actually do with it, right? So one base rule is one thing they can do with it. So first, what do? You can collect, let's say, out of 100 emails, 30 are spam. Okay, so let's say in total, you look at all the emails people get, about 30% of them are spam emails. So this tells you that P spam is 0.3. Okay, so this again by itself is not a very useful spam filter. You cannot randomly pick out 30% of emails and delete them, say they're spam. Okay, so this is not directly useful. But what you can guess is people have different rules. That says one rule is, let's say, short emails, let's say less than 50 characters, are more likely. Okay, so we can ask this question, right? So you may have a guess. For example, you may want to create a spam filter that has the following guess. You think, okay, very short emails I get are more likely to be spam. You don't know this directly, right? You don't know this probably directly. So the way you can figure this out is to use space rule, right? So what you can use space rule for is you want to compute, given the text is short, what is the chance this is spam? Right? Using all the information that's easier to collect. What you don't want to do is you don't want to ask somebody sitting there and say, look at this 100 emails. Look at all the short emails. Tell me this is spam or not. Classify the email. Okay, people don't do that. People just basically tell you the emails they think that are spam. Okay, so how can you use the information you have? Well, you can look at among the spam emails, all the characters, all the ones that has less than 50 characters. This you certainly can do. You have this whole class of spam. You can look at within this class, how many of them are short. Some fraction will be short. You can look at how many spam email do I have? Let's say 30%. This gets divided by, in total, how many short emails do I get? Right? So all these things are very easy to observe. Right? You have people whose class is spam. You can count characters in the email, certainly. Within the spam class, you can count characters. What this should do is, if this probably comes out to be very high, you now have a fairly good spam filter. This is how Lauder's spam filter basically is working by. And you have these guesses of what these rules are. You look at all the data, you compute using base rule what this probability is, and try to get a set of rules that has high probability. Okay, and you can do this without anybody manually labeling any data for you. You don't need to have somebody sitting there or looking at, a bunch of emails looking at whether your rules are correctly or not. You can just figure this out based on this block of data. Okay? This is how the spam filter works a lot like this. You're basically, if you have a power outage and your utility tells you how likely your power is come out, being restored within the next 2 hours or so, it's basically some rule like this. Yeah, especially applying this kind of rule. Based on everything I have collected, given some information I know about you, with the chance of something happening. Okay, so all this is rules that is built up this way. Again, these information are easy to collect. This is harder to collect, but you can compute it exactly using base rule. Okay, so this is hard. To directly observe, but can be computed, right? And the decision we want. Okay, right, so this is sort of the rules we have for base. And again, this is used all the time. You have a lot of data. This rule works pretty good. This rule works great. Okay, so one specific example we have working on with Seattle City Light and other utilities is to do this kind of thing. You have outage. So basically, you have a power outage. What people care about is my outage short or long? So you can say a short outage is something that gets restored within an hour, 2 hours. You have some go. And people want to ask, okay, is my outage short or long? Predict how long my outage will last. That by itself is not an obvious question to answer. Right? We don't have the specific data for a particular customer. And often it takes a long time to send out an engineer and look at your outage. But people want to know this thing quickly. So what can you do is some decision variables you think are important, for example, is let's say this depends on location. So maybe based on where the customer is, I can directly tell you that, based on where you are, maybe I can tell you whether it's a short outage or long outage, right? And the way to use base rule is you look at all the short outage you have, you look at where they have happened, multiply by the chance that your outage is short, right? So, and look at how many of these locations you have experienced. Right? So this is how a utility may tell you how long your outage lasts based on some information you get. And of course, in practice, you have a lot more information than just location. But it basically applies this kind of rule. If you take the big data set, you break it down to things you can observe, and you're trying to answer a decision question that's a bit harder to directly observe. Okay. Any questions with the base rule here? Again, base rule is a fundamental. Knowing this saves you a lot of time. Many times people go and basically try to label something like this. This is labor intensive, costly, and so on. Ignoring that they already have a lot of data. So whenever you have this sort of decision you want to make, the first thing you ask is, can I do a base rule? Do I have enough data to use base rule? If so, this ends up working very good. This is not a bad decision rule. Okay, so of course you can do a chain rule for base rule, right? So you can have many concurrent conditions. Right, so if you think of a span, of course, we don't just classify an email being spam or not based on how long the text is. You have many sort of conditions you think is important. So you often ask this kind of question. Let's say A is some event you care about. And you say, okay, what is the probability of A happening given all these things has happened? And you have n concurrent conditions. Okay, so suppose these are all true, what is the chance of A happening? Okay, suppose these are. Right, so in the outage example is, there may be time of day that matters. There may be your location that matters. There's all this kind of thing. So many conditions. And then what you can do is you can basically expand this into a product of rules. You can expand this into a product. So assuming CIs are independent, and basically you can divide this conditional probability, you can turn this around into a product. And the factor in front, this is just normalization. So the probability comes out to be between 0 and 1. Right? So that's just a normalization. But the key idea is conditional probability can be turned around. Okay? Conditional probability can always be turned around. And depending on which data you have, you want to calculate in the correct direction. Okay? So this is all naive base rule mean. Right? So you can now make this into a classifier. And the naive, in naive Bayes rule, this just means that as independent. So of course, the conditions you have may be sort of correlated, right? In cancer, so this is again, a lot of medical study goes like this as, what is the chance of you having cancer given that you smoke or you don't exercise or you don't eat very well, you don't eat very healthy, this kind of thing. So of course, often these are correlated, but their correlation may be very hard to figure out. So naive Bayes rule just says, let's not worry about whether they're correlated or not. Just let's pretend whether you smoke or you exercise has nothing to do with each other. So that's naive, right? It's a simple assumption. But in practice, this works very, very well. Okay. So in practice, okay, so this kind of condition may or may not be independent, but it does work fairly well. Okay. Right, so in the decision rule turns out to be the following. The decision rule is just that we have data, x1, xn, outcome y. So here, if you want to think of an example is we have x1 to xn. This is as maybe smoking, exercise, eating, healthy. Y is, let's say, you want to predict that somebody has cancer. Okay. So the observation when you go to your doctor, this goes like this. You fill in a form, whatever you do. What does the doctor wants to compute? Doctor wants to compute that what is the probability right? So you go to your doctor and say, okay, given all this information I'm telling you, is it more likely I have cancer or not? Okay. This is a very common question you ask. Good. Right. Oh, so independent means this is a product. This right. So you don't have a cross term of C1, C2 here. For example. So yeah, so it's not exactly zero. It's just that we don't need to consider product of C1 and C2 given A, C1, C2, and C3 given A. So if they're not independent, this is actually a more complicated looking formula. Just the formula is more complicated. So you never care about C1 given C2. If they're not independent, what happens is this product becomes and C2 given. You have this kind of term showing up in your product. Right. So based on A, what are these or many things that happens? Right. So in this example is right, given that people have cancer, it's sort of fairly hard to figure out, as all these things related to each other, and then more likely, given that the fact you're smoking, that you're not exercising and this kind of thing. Okay, so in principle, these are all related to each other, right? There's some, these factors are not completely independent. But normally in this kind of decision rule, often we just treat them as independent. It's an easier thing to count. Right? And really what you care about when you go to a doctor is you ask this question. You're filling out your form, doctor comes in and says, okay, I think it's more likely or less likely you have this disease. Right? This is a lot of times how medical diagnosis works. And in practice, in energy and in many other engineering contexts, well, you have this many things. What's the chance of this outcome happening? Right? So you observe. So in power grid, this has been used, for example, in cybersecurity. You observe this weird event in your grid. Is it undergoing somebody hacking it or not? What is the chance of somebody trying to hack it? Okay, so you have all this kind of question you want to ask. And the question you want to ask is the following is, which one is larger? Right? So the question really want to ask is P or Py equal to 0. Right? So given those things you have observed, which one is more likely to be true? Tell me which one is more likely to be true. Because Y is a binary condition, so the more than likely 1 is true, more than likely 0 is true. Okay, you want to do this kind of classification. So you have this kind of data. And under the naive base truth, it's actually quite easy to compute. Because what you can say is, well, Py given x1, xn, this is P, some sort of normalizing factor that in front, Py, xy given y, xn given y. Okay, so this is the cancer example is you got entire population within people, how many people have cancer, if they have cancer, how many people smoked, and so on. This you can compute. Okay. All right, so what you do, your decision is you compare which one of these is larger. You have probability of y being 1 multiplied by P you compare which one is larger, and based on which one is larger, you declare which one is more likely to be true. So if this one is larger, you declare y equal to 1. If this one is larger, you declare y equal to 0. You write out conditional probability and pick the one that's more likely to happen, given the observation x1 to xn. Any questions about this one? Good. Oh, okay. So when you talk about probability, this has to be a number between 0 and 1, right? So when you multiply this thing out, you normally need to divide this by some number. So you have to divide all these things by some number to get the true probability. You're missing a constant. There's some constant factor. So if you go to the two condition case, right? So this is basically your normalizing factor. Right? Yeah, PA, PP gonna divide by PB to come out to be the correct probability. But when you're making comparisons, so the nice thing is that this factor is on both sides anyways. Right? The same normalization on both sides. So when you're making comparisons, it doesn't matter what this normalization factor is. It gets canceled out anyways. So you just want to know without. So you don't need to worry about what this constant is. You only worry about which one of these is larger. Yeah, you don't care. Right? You're comparing the same normalization shows up on both sides. Right? It's the same number that shows up on both sides, multiplied by both sides. So it doesn't change the relative magnitude of the two things you're comparing. Yeah, we don't compute it. Right? So the decision rule is this. You can compute it if you want. It doesn't matter. You can any number here doesn't change your decision. Right? Whatever that number is has no impact on your decision. You compare the two things. So you don't need to compute that. No, right? So at the end of the day, again, you're comparing two alternatives, right? So your decision is either this one or this one. So you only care about the relative, right, number, right? So which one is bigger? Basically, you're trying to compare. If this thing is bigger than this one, you're going to declare that y is 1. If this is bigger than this one, you're going to declare y is 0. Right? You're making a decision given the observation x1 to xn. Right? So you're not saying a real number out of this. You're basically just a binary choice you're making at the end. Right? So make a binary choice. You just need to know which one of these is larger. There are questions? So why do you want a larger number? So the probability, right? So you declare there's only two things that can happen. One is either 1 or 0. And you say if it's more likely to be 1, you say it's 1. It's more likely to be 0, you say it's 0. Right? The classification, right? Yeah. Yeah. Just making you say classifier decision. Other questions? Okay, so again, Bayes rule, this is a lot more powerful than you would think from that. Right? Bayes rule has been around for hundreds of years for sure. And still that sometimes we're underappreciated. You can by computing sort of simple probabilities, you can make pretty good decisions in Bayes rule. So for one example, before we take a break, is to show you this, right? So again, this is red and blue classification. Okay? And you can train a logistic classifier on red or blue, or you can simply do a naive Bayes rule. So what Bayes rule does is, well, you compute, given where these points are, what the probability of one red or blue. And turns out your Bayes rule will actually do slightly better than the logistic regression. Okay? And this Bayes rule requires no training. It's a direct counting of how many points are there. Okay? And in this case, that does better than logistic regression. Okay? So in many, many cases, the Bayes rule does quite well. Just by looking at the data you have, and without doing any fancy method or separation or anything like that, you can do very well in Bayes rule. Okay, so naive Bayes rule by itself nowadays doesn't show up all that much. But if you look at a lot of the sophisticated models we have, Bayes rule is embedded somewhere in there. Somewhere you have this Bayes rule. So what happens is takes into account of the prior knowledge of something that's more likely to happen. Okay? You have to guess. And what is a more likely thing that's supposed to happen? Okay? So you write your your emails now have auto-completion. Basically, it's this kind of rule. Given we have written, what is the most likely thing you will write in the future? Just computing essentially a Bayes rule on that. Given all this large body of text, look at, given this phrase, what is coming after it, and deciding which one is more likely. Right? So Bayes rule is again incorporating a lot of Mercedes models. So something useful to know. Okay? So something that's very useful to know. Okay? Good. All right. So let's take a break. Then we'll look at sort of more, I guess, more advanced techniques. So in addition to logistic regression and Bayes rule, what are some more advanced techniques that we can do? Okay, so we'll look at sort of more complicated classification problems. All right, guys. All right, let's get started again. Okay, so we'll continue to look at the classifiers, but looking at the more complicated ones as we go forward. Okay, so the problem with some of the challenges with the ones we have seen so far is that the naive Bayes works well if the features are simple. If their features are categorical things like whether you smoke or not. Right? So these are where the naive Bayes rules works well. Naive Bayes tends not work so well if the features are complicated. And logistic regression So logistic regression does work well, but it's challenging to users if you care about sort of classifying something that can have more than two categories. Okay? With a standard test set being this MNIST data set. Okay, so MNIST just means that this is handwritten digits. So what do you want to do here? Each input is a 256 pixel image with 8 sort of grayscale levels. So each time you basically get a picture like this. And your goal is to put into 10, one of 10 classes, right? The 0, 1, 2, or 3. So you observe, you give them a picture like this, you try to get a computer to say this is 3, right? You get something like this, you try to get to say this is 7, and so on. This is a classical example. You have that. This is considered to be, used to be a very hard classification problem. Because the input is fairly high dimensional, right? Each input is 256 multiplied by 8. So it's fairly high dimensional. A lot of numbers in the input. You have many classes as output, right? So how do you classify this? This is a long-standing sort of canonical problem people are trying to solve. And basically, deep learning became popular because it solved this problem better than everything else. But before going there, why is this important? There's a good reason why this is an important problem. And solving this better has sort of direct consequences. Right? Not exactly bank checks. No, those are printed. So not very hard to write. You can hide write, but when you write a check, you're writing words, right? Not directly numbers. So this is not exactly check. No. We're in good. But that's later, right? So once this took off, then people said, oh, I can do computer vision, I can detect objects and things like that. But specifically, why is recognizing digits important? This is not asking to recognize written words. This is specifically asking you can recognize from 0 to 9 handwritten digits. Where does this happen? Where do you have handwritten digits? That's important for a computer to recognize what it is. Right, so when will you scan numbers? What is the context? You will scan just numbers, right? This has no care about letters. I don't care, right? So you don't have to recognize ABCD. All I want you to do is give me a very high probability of being correct of 0 to 9. So where this came out is this basically zip code. This came out because you really want the computer to read the zip code when you're sorting mail. So in postal mail, the way you sort it, you take all this mail. Based on what the zip code is, you sort it where it's supposed to go. The exact address is okay. The delivery person will basically look at the address and give it to each address. But the zip code, you want the machine to sort it into buckets and automate this process. You don't want humans to read all this mails, basically. And in the 70s and 80s, I think each percentage of postal mail that you recognize correctly is some billions of dollars saved manual labor. There's so many emails with postal codes on there. You don't want humans to read it. You just want a machine to take all the letters you want to mail and sort them by itself. And that's really where vision first took off. So it's not automatic driving or robotics or anything like that. It's basically when you want to send something through postal mail, can you recognize the zip code that's on the letter? That's where this basically data set came from. Okay, so people handwrite zip codes on your letters. You really want a machine to sort it. You don't want some poor human sorting this. Okay. So nowadays it's obviously not as important. Right? So one is, this is now an easier problem. We don't have that many postal mails, and we can recognize, much harder vision problems. But still, this is sort of humble beginning of vision. Basically, given 5 numbers, can you tell me which 5 numbers these are? That's really what you want to do in this video. And this was hard. Like this is by no means easy. Right? For a computer, this was tremendously difficult. The reason is people, right, can write a 7 this way. People write 7 this way. If you write 7 like this, people sometimes rotate this. They don't write straight up and down. They write at the angle. Sometimes one is larger than other ones, all this. So this was classical example is for humans, because this is not a hard problem. For computers, this would be an extremely hard problem. But nowadays, computers can basically beat humans in some sense. So computers are more correct than humans. But when we say a complicated classification problem, you can have this in mind. You have a 256 times 8, basically vector as input. Output is one of these 10 classes. Question? Any questions for this example? Yeah. For each individual one. So this is a pic. This is 16 by 16 pixel, right? So that's 256 pixels. 8 is the grayscale image levels. Right? So each of these is. So let's say this thing. This is 16 by 16 pixels. And then you have 8 grayscale levels. Okay, so basically you have a postal mail comes in, you have a camera taking a picture, dividing into 5 ones, and this is how large the picture is. It's again not super high resolution, just 16 by 16 pixels and black and white picture. Okay. No. Grayscale is how dark or light this is. It's black and white, right? Grayscale is the intensity of the darkness. Right. So each picture in total, right? So each picture is 16 times 16 times 8 dimensional. Right? There are 16 locations where I can put a number. Each of these locations, I can put a number between 0 and 7. Right? Okay, so this is, the dimension is actually quite large. Okay, this is just a small picture, and it's black and white is this large. We can imagine in a vision problem, everything of this here is big. Right? This again, people started with this example. And you can think of in the 70s actually, right? Why are these all 16 and 8? This is basically the hexadecimal. You can read. Right? This is a limitation of hardware, why these things are still very small. And nowadays it's larger, but this really started in the 60s and 70s. You have people building this kind of thing. Any questions? Yeah. They're all 16 by 16. So each of them shows up as pixel 16, 256 pixels. This is a picture. This is a picture with 256 pixels on there. Right? On each of them, you have this kind of digits written on them. Right? So if you want, you can think of this a vector with this many dimensions. It's a very high dimensional vector. Okay, good. Right. So yeah, so this is something to keep in mind when you say, think of again, today this is not very complicated. This is for a small input, right? But again, still it's more complicated than the method that we have talked about. The method we have talked about really doesn't work too well for this. Okay. For logistic regression, again, there's 10 outcomes. It's hard for you to tell you which 10 outcome this is. Bayes rule has trouble if your input is this large. This is too large dimensional input for Bayes rule. Okay. So the idea, the first thing we did is, so the method that people used to use to deal with this sort of more complicated classification problem is if you think back to logistic regression. Logistic regression, what always doing geometrically is basically trying to separate 2 classes of pictures. And then what people realized is it's okay to directly just think about separating classes of dots. Let's forget about the logistic regression, forget about logistic function and things like that. Let's just try to separate dots directly without going through this 1/1 plus e to the minus w transpose x business. Okay? Just see if how likely can I get this correct. If I give you two classes of dots, one blue, one red, can I draw a line that separates it? That's all you want to consider for them. And this gives you something called the support vector machine. Okay, so this is explicitly separating the line. Right? You have a bunch of lines, you want to draw something that separates them. And the word support vector machine is a word that's invented, this is called SVM. It's basically invented to make it sound fairly fancy. So the idea is, let's say you have some two class of dots, some blue dots and some red dots. And you want to draw a line, cross them. Separating them. In this case, you can easily draw a line. Okay? So this line will separate the two classes. A new dot comes in, you look at, on this side, you say it's blue, on this side, you say it's red. Okay? So you can call this a linear separator. It's probably a better name. The support vector machine is saying, okay, if I just call this a linear separator, this is doesn't sound fancy enough. So I want a fancier name for this thing. So I'm going to call this line the support vector. You can, in your mind, think of just line separating the classes. There's a fancier name for this, it's called a support vector. This sort of supports your separation of the two classes. Machine is just a machine, right? So you put this into a computer will give out to you. So that's why I call support vector machine. Again, now, at least right now, you can think of as given two classes, put a line through it. That's where the name comes from. And support vector is just a fancy name for this line separating the two classes. Okay. So, and often nowadays, you see this as a SVM, support vector machine. So this works better for multiple classes. And sort of have an easier interpretation. The easier interpretation being that directly this is separating the 2 points. Instead of going through logistic regression, getting to the cross entropy loss and optimizing that. Here you can directly ask for this, geometrically ask for this line. And this was, before neural networks become popular, this was the sort of the best thing you can do for the MNIST data. Okay, so this, when I draw like this seems very simple, but it's still a quite powerful idea at that time. Yeah, go ahead. Oh, yeah, so we'll get to that later. So we'll do the binary case, we'll get to the multiple classes later. Yeah, we'll get to that later. Okay, so let's do the linear sort of support vector first. And what linear SVM NASA is saying that we have features X in Rn, right? So if you want MNIST, the handwritten digits, n is 256 multiplied by 8. So this is how large n can be. Okay, right, so when you have the MNIST picture, right? So you have this picture that's two-dimensional. But when you think about it, it's just a long vector. That's just your input vector. Okay, so you can make it into a huge vector and think of that as your feature. That's so mathematically, that's a fun way to think about it. But for now, let's say we have binary labels. Okay, so still let's say we have binary labels. And here, instead of saying that y is 0 or 1, it's either think it is either -1 or 1. Okay, so again, it's binary, so you can call this whatever you want. In this case, it's mathematically easier to think as minus 1 and 1. And your classifier, basically, you take x, you compute this number, W transpose x plus b, and you compare this value to 0. If this less than 0, you say y is minus 1. If it's more than 0, you say y is 1. Okay, so this is your classifier. Is you're supposed to get some vector w, some bias b. And when you decide it, you just put in x and do this computation and see the value, whether it comes out to 0. Compare the value you get against 0. Okay, so this is the classifier that you want to use, right? If you know w and b. And the reason we call y minus 1, 1 is we want to use the following function. Or let's say that y is a sine, where the sine of a number is just 1. Okay, so this is just a sine function. Basically, is a number positive or negative. So you just want your classifier. As you do this computation, you look at whether it's negative or positive, and then you make a decision. And the benefit of SVM comes from the following observation. Is if you look at two classes of points, typically there are, in this case, there are many separators you can have, right? So all of these perfectly separates these two classes of points. The question is, which one do you pick? Right? So we have two classes of points. Now, this line separates them, this line separates them, this line separates them, and so on. Which one should you pick? Another idea? So how will you pick it? Right, so the idea is basically correct. The idea is you want to pick a line that is a maximum distance from both classes, right? Somehow you want to pick a line that is far away from both of them. So this line is no good. Maybe it's too close to this one. Right? So this line is no good. It's too close to that. So somehow you need a notion of distance to say that my line is the best if it's equally far from both. That's the idea, right? So maximum distance from both of them and separates. This is hard to do with logistic regression. In logistic regression, it's hard to have this sort of maximizing distance idea. However, in SVM, you can directly define the distance. Okay, you can just this is Euclidean distance in this case. Define the distance and find the one that has the line that has the largest distance. Yeah, good. Oh yeah, can go whichever way you want, right? So in this case, they just this is one. This definitely is another one that separates, right? So given all these planes that's possible, you don't find the best one. Right? The best one is again the one that's far away from both. That's the best one. It turns out in this case is this one. Right? But definitely this is another line that will separate. Right? So you want the best one. And that's really what's good about SVM. As you have this notion of what the best plane is. It's a very direct interpretation of the best. It's for the largest distance is. Okay. Any questions? Okay, and the SVM is basically saying that. Right, so the idea to get the best way is to think of the margin between. The margin really is you have a separator. If you have this separator, you want to look at when. So if you move this thing up and down, if you sort of scale this thing up and down, when do you hit each of the classes? And you want this margin to be large. The larger that margin, the better your line is. Okay, so you want to say anytime you have a separator, I can move this thing around until it hits one of these points. So I want to move in such a way that I can capture the idea of the margin between the two classes. Okay. But the idea is given. Okay, so let's suppose. Okay, suppose this thing is greater than 0. Suppose I have a plus some w and b, this thing larger than 0. I can always scale this thing for this to be exactly equal to 1. I can always scale this thing to be exactly equal to 1. And the idea is that if you need to scale this thing a lot to get to be equal to 1, then we say this is a large margin. Right? So this is the idea that we have. So if you look at geometrically this margin, what it turns out to be is if you have 2 points on the boundary, basically, on this point where this is equal to 1, this point is -1. You want this distance is large if the norm of this W is small. Turns out this is what the geometry turns out to be. Right? So basically, the norm of W, you can think of as how hard you're trying to multiply by x to separate out this two. So the larger the norm, the larger you have to make this number to get to be 1. If the smaller the norm, the smaller this number needs to be, and a sort of larger distance. So the way for 2-dimensional is a bit complicated, so you can look at this example. Okay, so suppose you have 2 points here, right? So we're going to take a very simple point. We're going to say this is 2 points on the line, just on the real line. This is where 0 is. Okay, so suppose this 2 points is 0.1 minus 0.1. Okay, right? And I want to separate them, right? So I want some W that separates out them. So here to get W is times x equal to 1. W has to be equal to 10, right? So here 10 multiplied by 0.1 gives you 1. So here you have notion of W is 10. The weight is 10. Now you can say that suppose the 2 points are further away. I say this is 0, this is 10, this is minus 10. Then Wx equal to 1, W just needs to be 0.1 in this case. Right, so W equals to 0.1, you can make W times x1. So the size of W, this vector, tells you how far apart these points are. So the smaller the W, the further apart they are. The larger the W, the closer they are. So our idea of how separable these points are is inversely proportional to the norm of W. In high dimensional, this also holds. Okay, so the norm of W just gives the idea of, so of course the point being between minus 10 and 10 is easier to separate than minus 0.1 to 0.1. Okay, so W just gives you a measure of how hard it is to separate. And this is inversely proportional to the norm. Okay, so you want a separator and you want the norm to be small. Whenever you have a separator, you want the norm to be small. The smaller the norm, so the more distance you have. Okay. And this is basically the SVM, this is the condition. This is a problem for SVM. As you classify the points and you ask the weights to be as small as possible to classify a point. Not in turn maximize the margin. So the optimization problem is that one, they want to classify the point. Two is you want to max the margin. Okay, and we say that a point is classified correctly Okay, so this is, we say this point is classified correctly. So remember classifier, this is either 1 or -1. So if y is 1, you want this to be positive. You can always make this, any number, positive number, you can scale to be 1. If y is -1, you want this to be negative. Negative multiplied by negative should still be larger than 1. Okay, so this is what I mean by a point is classified correctly. Okay, as yi multiplied by this thing should always be bigger than 1. Any question about this equation? Okay, so this 1 again is you can take this to be any number you want. We just pick 1. Right? Okay. So this thing, the sign of these two has to always be the same. Right? The sign, our decision rule is the sign of this number gives you y. So they must have the same sign. And then the optimization problem becomes, okay, so this is our optimization problem. And find me a classifier, W and B, such that all the points are classified correctly where you have the minimum norm. And this turns out to maximize the margin. This turns out to be the one that is the line that sort of furthers away from both class of points. Okay, so this is what SVM comes out to be. So of course, you're not going to be asked to solve this. But again, when you run this code, underneath your code is some solver solving this, basically. And there's many ways to solve this thing fast, basically. Then this is not a super difficult problem to solve. This is a convex problem. Yeah, this is a convex problem you can solve. So this is not terribly difficult to solve, but this is the idea what SVM is solving. And again, the benefit of this is this directly maximizes the margin, saying that if I have a separator that's further away from both classes, it's easier to interpret than logistic regression. So you're not quite sure what logistic regression is doing, but this you know geometrically what it's trying to do. Any questions about this one? Okay, so the next thing is the interesting part. As if you look at this condition, it says that I have to classify every point correctly, right? I have to classify every point I have correctly. What happens if this is not possible? What happens if your data point is something like this? So you have some green points like this, and you have some red points like that. They're almost separated, but not exactly. Right? So there's some sort of mixture of red and green. So you cannot draw a line that separates out every point exactly correctly. Right? So again, there's a nice interpretation of SVM. There's a nice way to deal with this. Any suggestion how to deal with this? So very often in practice, your answer cannot be exactly right. If you look at head, yeah, go ahead. Right, so I want the computer to do it. I don't want to do it. So how do I get a computer to separate things when they're not exactly separable? Right? So, yeah, so you don't got to move this, right? This is the data you have. So you're not right now moving the data. Right? So this similar with the handwritten digits. There's nothing that recognizes 100% correctly as handwritten. Right? Your goal is to maximize the accuracy, not ask for 100% correct. Humans cannot recognize 100%. Right? People just write wrong numbers sometimes, right? So just not correct numbers. Okay. So the way to do it is you introduce something called a slack variable. Okay. So what you do is you allow wrong decisions. But you want to allow sort of small number of wrong decisions. So the way you do this is the following. And you say that, well, if you look at the original problem we have, So let's say this problem is too hard. You cannot always scale this thing to be above one. It's not separable. So you cannot always do this. So what do? Well, you let it to be wrong. Okay, so you introduce this called a slack variable. It's just that if you're wrong, it's okay. If you're wrong, this is okay. But I'm going to penalize you for being wrong. So you can subtract some number. So this is a slack. But what you do is you add and okay, so SVM is you allowed to have some slack, right? So there's some slack you can have here. Okay, so for example, if Z is very positive, then this is very easy. Okay, so this is easier to satisfy if you subtract from the right-hand side a positive number. Right? The inequality, so subtracting from the right-hand side, make it easier to satisfy. Anytime you have to subtract, we're going to penalize you. So when you optimize, you tend not to subtract too many. Okay? So you're allowed to be wrong, but essentially this gets you penalize this heavily. So only use Z if it's absolutely necessary. It doesn't want to use Z, but it's allowed to make mistakes. Right. So this is the SVM that we tend to use. Right? We can use. Okay. Okay, so you're allowed to be wrong, and basically you're solving this an optimization problem. So if you have an example, for example, you have sort of red and blue all mixed together, you can pretty easily find some linear separator. And the benefit of linear SVM is it can be solved extremely efficiently. So this means that, millions of data points, hundreds of dimensions can be solved in sort of trivial amount of time. Okay, we really, really, really got good at optimizing how we solve this kind of problem. So if you ever take optimization, you recognize this class of problems. But if you don't care about how you can solve them, we can solve it very, very quickly. Okay, millions of points, thousands of dimensions takes your computer will do fine solving this. Your computer have no problem solving this. Okay, so compared to some sort of more modern machine learning techniques, may take you say a month to solve one model. This thing takes you a few seconds to solve. Okay, so again, if you want easy answers, you run this kind of thing first. Yeah, you run this kind of thing first before you move on to any more complicated models that you have. Any questions with SVM? Yeah. Yeah. Oh, why does it have to be greater than one, right? So remember our classifier, go to the basic classifier, right? So if this thing is larger than zero, we say it's one, right? Less than zero, we say it's minus one. So y is the sign of this number, right? So this thing and y, if it's classified correctly, it will have the same sign, right? When you multiply them together, there'll be a positive number, right? So if it's a positive number, I can always scale that number to be one. Right? I can always, multiply this, make W larger for it to be one. Right? Is that right? So that's why I say it's classified correctly if this thing multiplied by y is larger or equal to one. So there's yeah. Y is your label. Yeah, y is your label. Right? So you classify into so y is one or minus one. That's the label. Okay. Good. Any other questions for SVM? Yeah, SVM works for a lot of times. Like a lot of times your job SVM work perfectly, especially if your data set is large. So let's say you're working for, so in, I guess in energy, you may or may not have this kind of large data set. Yeah, energy sometimes a very large data set. The energy, especially you have phasor measurement, your data set can be, terabytes per day data you get from the system. And then if you have terabytes of data per day, sometimes SVM is the only thing you can run, the only thing that will run in time to process your data. Okay, so often that's you use this kind of technique because you can solve it very fast. Yeah. Any questions for SVM? Okay, so SVM works, and we'll skip this sort of kernel-based classification because this is tied into neural networks, which we'll cover sort of together next time. But in this class, we'll finish its way to just saying how do you extend this into more than binary classification, right? You have the MNIST data asks you to classify between 0 to 9. Okay, so SVM so far is still binary, right? Still 1 or -1. So any ideas? How do we say extend this into multiple labels to classify into? This is actually where SVM is better than logistic regression. Logistic regression is very hard. It's sort of kind of hard to think of how do you extend. SVM actually you can do. Okay, so for SVM, what you're gonna do is the following. One way to do it is the so-called one against all. And the idea is simply the following is you have K classes. Right, so think of, in MNIST, K as 10 classes you possibly care about. You simply train 10 K SVM. Okay, so what does K SVM mean? You basically have W1, B1, WK, BK. Okay, you train K SVM, you got all of these, right? So each SVM basically is a W vector plus B offset, W vector plus offset. How do you train this? So for each class, you say the following. So for the M's SVM, your yi is now labeled the following. Okay, so what this means is you have handwritten digits. Your first SVM you train is basically asking, is it 0 or not 0? That's how you label your data. Second SVM you train is the handwritten digit 1 or not 1. Okay, so you can turn this into a binary classification problem for each of the handwritten digits. Okay, so you go through them. Is this my class or not my class? That's the question you're asking. Instead of asking which one is it, asking is it 5 or not 5? That's all this. Okay. So what do is you're given a new x, right? You pick the k that maximizes Wm, right? So you have mk classifiers. Each of them, you get a new x, you can find this number. Whichever one is the largest by this number, you call that as the correct class you have. Okay. Each time when you do the classifier, this tells you basically how sure you are this is within your class. So you compute all of these, for the 10 classes you have, pick out the largest one. Pick out the one that is sort of most sure of it is within that class. Okay. Right. So optimizing over. Right. So you have so in the MNIST data you have 0 to 9, right? So you basically let's look at the MNIST example. We have W0, B0. Right, for the 10 of these. You have a new picture, new handwritten digits comes in. You're going to compute this thing 10 times. Whichever of this comes out to the largest, you say that's a class of your picture. Okay? So because the way you're going to interpret SVM is, but if you're very, very sure it's in your class, then this thing is big. You're very sure that this just gives the idea of how sure you are. This product is very big, you're very sure it's in your class. Okay, so you can just join 10 of them and decide, look at each of this product and say which one is bigger. Okay, so how many classes you have? You have this many classifiers. Any questions about this? Okay, so again, you turn into a binary decision problem. You basically, this is like taking a majority poll, right? Whichever one you think is not majority poll, but this is looking at which one is the most strongly they think you think is in this class. That's a class, right? So M that maximizes, that's your class. Okay. So this is saying that which one of these is think is the most likely to be right. Okay. So the benefit of this is you just need K classifiers. So it's not overly complicated to train this. Okay. It doesn't improve your it's not that overly complicated. The drawback is often that none of this is very large. This is not a poll. This is basically you asking some question in class, let's say, and whoever yells the loudest, you say that's correct. And it's basically you have K classes, whichever one is the strongest, largest, you say that's correct. But sometimes what you really want is you want to poll, you want to take a majority poll. Yeah, so this is not a majority poll. So the other classifier that does better is you call a one class, one against one case. So this basically trying to take a poll of the classifiers. This is a majority vote. And the way you do this is you have K classes. You train pairwise classifiers. Right? So with pairwise classifier means that for each I and J, or for each M and N, you train classify. Okay, so again, in the in this case, you train classifier is it 0 or 1, 0 or 2, 0 or 3, 1 or 2, 1 or 3, this kind of thing. Okay, so each time it comes in, well, you're not asking directly which one is it. You're asking, is it more likely to be 0 or more likely to be 1, more likely to be 0 or more likely to be 2? You're asking all of this questions at the same time. So what that gives you is you have k minus 1 over 2 classifiers in total. Right, so each one of them will output a class. And the end of the day is you pick the class that wins the most. Okay, so you have all of this k times k minus 1 over 2, basically pairwise comparisons you do. Whichever one that wins some, right? So let's say 5 wins the most, you say this image is 5. This digit is 5. Okay, and this is basically majority vote, right? So every binary choice gets a vote. Whoever gets the most vote wins this. This is much more robust than if you just take the one with the largest value. This is quite a bit more robust. And majority vote typically works in a lot of cases. Any questions about this one? So these are sort of the classical ways to figure out, given multiple classes, which one it is. But the drawback, obviously, of this one, this is a K-score. Right? You have to train a lot of classifiers. So digits, probably okay, right? There's not that many classifiers. But you're doing something more complex like computer vision, where you're trying to recognize handwritten characters instead of just digits, where you recognize 26 letters, then this becomes too large to train. You cannot really train that all that well. Okay, so we'll stop here today. Next class, we'll see neural networks and basically see how neural networks will overcome some of the drawbacks here and directly outputs which class it is. And we'll see sort of how you optimize that to get the sort of better performance and the linear classifier. Okay, so we'll stop here today. You'll do some homework questions for linear classifiers. So it's fairly straightforward. And the next time we'll start with neural networks. Okay, thanks guys.